I want to record a couple of more examples from this number 2 on week 1 notes, okay? Rational functions and all that other stuff. I only went to number 2 because of the sake of time. Otherwise, notes can be very, very long if I were to work out every single example with all the details. And again, we're not trying to inundate you with more than an hour and a half of video notes. But if you do have questions over specifically number 4 and 6, you can watch this video to get those answers. Okay, so let's go ahead and look at this. Again, we are doing the premise that we're trying to figure this out from a pure rational form, and we're going to try to graph the attributes of this function of where it exists all by hand. Okay, so let's go ahead and start with number 4. We know that the first rule is to factor. So we see a difference of squares, which is x plus 3, x minus 3 up top. We still have an x minus 3 on the bottom. This is our factored form of our pure rational expression, okay? So we identify immediately that there's a hole in the graph at x is equal to 3, because the hole, again, exists when I find a pair. So I factored, and then I went straight to the removable discontinuity. From other examples that you saw on the videos prior, we saw the acronym VAD-HARD as far as all the different attributes that we're looking at, okay? And the removable discontinuity, again, we just identified occurs at x is equal to 3 because we set this little piece, this little x minus 3 equal to 0, because we're setting everything equal to 0, and then we solve for x. This is our removable discontinuity. Now, here's a big step. If this were to go away and x plus 3 was left over, so let me do that again. If this went away and x plus 3 was left over, this is like x plus 3 over 1. That means the leftover pieces would just be x plus 3 like a graph, y equals x plus 3. So if I said graph that, well, you would go to 3 with the slope of 1 would look something like this. Okay, so it would look like a graph or a line that went through 0, 3, had a slope of 1, but the catch is that it has a hole at x is equal to 3. So way up here at x is equal to 3, there's going to actually be a hole in the graph, which we will not end up writing anything there, but just a small little hole that shows that it's open. Now, if I asked you to solve for this hole by hand, well, you would take this removable discontinuity right here, and you would basically plug it into the piece that was left over after the hole in the graph has been removed. So if I plug in 3 here for x, basically right here, well, 3 plus 3 would give me 6. So 3, 6 is where the hole in the graph would exist, which is what you see exactly right here. Okay, that's where the hole would exist. Now, there aren't any leftover factors in the denominator, and because of that, there's nothing we can set equal to 0 to find the vertical asymptotes. So we're going to go ahead and put none for that. So the only place that this function isn't continuous, the only place where it has a break or a hole in the graph or some kind of jump, if you will, is going to be, again, when my denominator is equal to 0. So the only ones that exist are at x is equal to 3. Again, other slides and other examples, we show the VA and the RD, but here we only have the RD. So we're going to say that the x is everything except for that positive 3. And again, if you wanted to do it in interval notation, you are more than welcome to, because it means the same thing. Now, the horizontal asymptote. The horizontal asymptote is going to look at the original standard form that was given, and we're going to use Bobo, Botu, Betsy. Okay, which means we're going to look at the powers first. Look at the powers of x first. And you notice that the 2 is bigger than this understood 1. So it's bigger on top. Okay, so that's Bo2. And Bo2 is bigger on top. It's going to be undefined. Otherwise, undefined means that there's not going to be a horizontal asymptote. So we'll just put none. Same as undefined in this particular case. Okay. And last but not least, the range will come from the horizontal asymptote, if it has one, and that y value of any and all of the holes that exist. So With those two combined, the only y value that you wouldn't actually see on the graph is this y is equal to 6. That's the only break as far as y's is concerned, that the range would not exist. So we're going to put y's that are not 6 or negative infinity all the way to 6, union all the way to infinity. So you would say it's 6 to infinity. Either way, it's still the range, okay? And then the last thing that we need to just graph would be the x and the y-intercept, okay? So the y-intercept is the easier one because we plug in 0 for x. So if I plugged in 0 where x is at in the original equation, it would give me a negative 9 over negative 3, which would be a positive 3, which is what we have drawn right here. And then the x-intercept is whenever, again, in the factored form, after the wholes have been accounted for, all the remaining pieces in the numerator have to be set equal to 0, okay? So if I set this x plus 3 equal to 0, I'm going to see that it's going to equal negative 3 is where the x-intercept would occur. Okay, so x equals negative 3. And again, you could put negative 3, 0, and this one you could have put as 0, 3 if you wanted to do it as a point. Okay, so x is equal to negative 3. I drew it a little bit off scale, but it would actually go through the graph at negative 3. Okay, so those are all the pieces of what we have here. And just a quick summarization. Just because it looks like a fraction, like a rational expression or a rational function, it does not mean that it's going to follow your 1 over x default where you have kind of two pieces of this curved graph. It doesn't mean that it's going to have that. In this case, you see that this looks like it's y equals x, like a linear function, something we did a long time ago, okay? But that's only because this canceled out and this was what was left. We still accounted for everything. Let's find number 6. And the reason why I'm wanting to do 4 and 6 is because they are a little bit different and weird comparatively to the other ones. But what you see with number 4 and 6, you will easily be able to understand number 5 when you go to the notes, okay? So let's do number 6. Factoring is our first step. So we have the GCF of 3 that can factor out from the top, and I have a difference of squares on the bottom. Okay, so this right now is my not yet fully factored. It will be factored fully when I see the difference of squares, x plus 3, x minus 3 up top, and then x plus 3 and x minus 3 on the bottom. Okay, this is my fully factored form. Okay, so now let's go through the steps. We have VAD hard, so vertical asymptote, horizontal asymptote, domain range, removable discontinuity, and then I will put the x-intercept over here and the y-intercept over here, just because I don't have that much room right now. Okay, so just like we've done before, first step is to identify the removable discontinuity or removable discontinuities. So in this sense, we have there's a carbon copy and there's a different carbon copy. So for this one, the removable discontinuity would occur at 3, because we set it equal to 0 and solve for x. And here it would occur at negative 3. So x is equal to negative 3 and 3. Those are where wholes would exist. Okay? Now, if those canceled out and they're gone, the only thing that remains is this y equals 3. And it's like 3 over 1, if you will. And y equals 3, if that was the only thing that was left, that's like saying it's just a line at y is equal to 3 that looks something like this, okay? So that means y is equal to 3 is what it would look like. However, we have wholes at negative 3 and positive 3. So on this graph, at negative 3, where the graph would normally exist, I'm going to put a hole in the graph. And at positive 3, because my removable discontinuity said that's where I would have holes in the graph. Okay, so I'll put a hole in the graph there and a hole in the graph there. Okay, so with that being said, let's do what we did on number 4 back here so that we got number 6. Okay, so let me go back to 4, and right here for number 6, the way we got that 6 is we found this x value plugged it into the piece that would be left over, and then we found the value of 6. That's what we're going to do here. If we plug in -3 into what would be left over after those removable discontinuities canceled out, well, there's no x to plug in this -3. There's no place that I can plug in this -3. So it's going to give me just this answer that it has written as a constant of 3. So it'd be -3, 3. Okay. This, whoops, let me highlight it in green. The reason why this is 3 is because there was no x value that I could plug in this input value of -3. Okay, and that's going to happen the same over here. When I plug in 3 into nothing that has an x, it has to yield whatever this constant is right here. Again, that would be that green place right there, and that's me trying to input this value of 3. Okay, but nonetheless, what these are showing you is that -3, 3 is where the graph, if it existed, would be a colored in point at -3. But because it doesn't exist, I don't have to even label it. I can leave it a hold just the way it has right here. Okay, so now let's go back and let's ask ourselves, how do we find the rest? If we know where the removable discontinuities, how do we find the other pieces? Okay, so from here, what I would do is I would immediately, like before, other examples, I'd go to the vertical asymptote, which is what's left over on the bottom. What factors are left over that I can set equal to 0? Well, there's none. Okay, so you're not going to have a vertical asymptote. Again, even though it looked like a rational function, it doesn't guarantee it. We have to see these cancellations occur and see the scraps that are left over. Okay, the horizontal asymptote, we're going to look at our original one, and that's bet C. Bet C is going to be where its bottom is equal to the top. And I mean the bottom equals the top is the bottom power equals the top power. Those exponents are the same. Okay, so what it's going to be is it's going to be the coefficient, the ratio of it. Okay, so 3 over an understood 1, that would be our horizontal asymptote. But here's the thing. This one is not going to have a horizontal asymptote because it's the line that the graph would approach but actually never hit as you go to infinity or negative infinity, like we've discussed before. And this one, it would hit. It would hit all the time. It wouldn't just get close and then touch. It would touch all the time. So in this specific weird one, if you will, this is why there's going to be none for the horizontal asymptote as well. Okay? So again, there are special case scenarios, and this is why I chose to record number 4 and 6. And then the domain. Again, the domain is just looking everywhere where the bottom is not equal to 0. Okay, so we know the bottom is equal to 0 here at -3 and 3, as we showed here and here. That means x's that are not equal to -3 or 3, that's our domain. Otherwise, some of you might feel a lot more comfortable showing it as these intervals of -infinity to -3, then -3 to 3, and then 3 to infinity. And again, if you were interpreting it like a number line, or let me just highlight it. You're just talking about this is this piece, this is this piece, and this is this piece, as far as where it occurs on the x-axis. Okay, so let's come over here, and now let's look at what would the range be. So the range are, what are all the y values that you see on this graph? Okay, now this graph isn't going up or down, it's not increasing or decreasing, it's just a constant line. And even though there are holes in the graph that you see, if I asked you what y values do exist on this graph, you would have to say y is equal to 3. And only that. There's not an interval of any kind. This is only at y is equal to 3. And again, I know that there are holes in the graph, but here y is equal to 3. Here y is equal to 3. All other places y is still equal to 3. And if you at least have it once, you have to account for it. Just because you have a hole somewhere else doesn't mean, oh, we're not going to count 3. We have to account for it. Okay, so I hope that this does help. The x-intercepts, let me finish this off by saying the x-intercepts and the y-intercepts. Y-intercept is the easier one because you're just putting 0 in for x. So I'd have 0 over 0, and then this -27 divided by a -9, which is a +3. Okay, so y equals 3, which is right here, aka 0, 3 if you put it as a point. Okay, and then the x-intercept. This has no x-intercepts. And the reason of that is that in the factored form here, what was left over did not have an x. If it did, let's say it had 3x instead of just 3, then we could set this equal to 0, divide by 3, and say, oh, there's our x-intercept. It should cross on the x-axis where x would be equal to 0. Okay, but it doesn't have that x, it just has a constant, which means we can't set it equal to 0. We can't set 3 equal to 0 and then solve for x. There's no x to solve for. That's why we're going to say none on the x-intercept. So I hope this helped. Wanted to make it not required necessarily, but I want to put it and add it to the list as far as on the calendar in case you do have questions.